Welcome to today's lesson on acids, bases, and salts. This topic is very important in chemistry because acids and bases are found everywhere in our daily lives. Acids occur naturally in many substances. For example, citric acid is found in lemons and oranges. Ethanoic acid is found in vinegar. Carbonic acid is present in soft drinks, while lactic acid is produced in muscles during vigorous exercise. In the laboratory, the common acids are hydrochloric acid, sulfuric acid, and nitric acid. Chemically, an acid is defined as a substance that produces hydrogen ions, represented as H+, when dissolved in water. These hydrogen ions are responsible for all the acidic properties we observe. It is important to understand that acids only show acidic properties when water is present. For example, hydrogen chloride gas by itself does not behave as an acid. However, when dissolved in water, it ionizes to produce hydrogen ions and chloride ions. Acids can exist as concentrated acids or dilute acids. A concentrated acid contains a large amount of acid dissolved in a small amount of water, while a dilute acid contains more water and less acid. As we continue, remember this key idea. Hydrogen ions are the source of acidic behavior, and without water, acids cannot produce these ions. Let us now examine the physical and chemical properties of acids. Dilute acids generally have a sour taste. Although tasting chemicals in the laboratory is never allowed, they turn blue litmus paper red and conduct electricity when dissolved in water because they contain mobile ions. Acids react with metals that are above hydrogen in the reactivity series. During this reaction, a salt and hydrogen gas are produced. For example, zinc reacts with sulfuric acid to form zinc sulfate and hydrogen gas. The gas can be identified by the characteristic pop sound when a burning splint is brought near it. Acids also react with metal oxides and metal hydroxides. These reactions produce salt and water and are called neutralization reactions. For example, copper oxide reacts with sulfuric acid to produce copper sulfate and water. Another important reaction is between acids and carbonates. When an acid reacts with a carbonate, a salt, water, and carbon dioxide gas are formed. Effervescence, or bubbling, is observed because carbon dioxide is released. To test for carbon dioxide, the gas is passed through lime water. If carbon dioxide is present, the lime water turns milky due to the formation of calcium carbonate. These reactions are frequently tested in KCSE examinations, so it is important to master both the equations and observations. In this section, we focus on why water is essential for acids and how acids are classified according to basicity. Pure acids consist of covalent molecules. When these molecules dissolve in water, they ionize to produce hydrogen ions. This process is known as ionization. Experiments show that hydrogen chloride dissolved in water conducts electricity and reacts with metals and carbonates. However, hydrogen chloride dissolved in a non-aqueous solvent, such as methylbenzene, does not show these properties. This proves that water is necessary for acids to produce hydrogen ions. Another important concept is the basicity of an acid. Basicity refers to the number of ionizable hydrogen ions that one molecule of an acid can produce. Hydrochloric acid and nitric acid each produce one hydrogen ion and are therefore monobasic acids. Sulfuric acid produces two hydrogen ions and is dibasic. Phosphoric acid produces three hydrogen ions and is tribasic. We also classify acids as strong or weak. Strong acids, such as hydrochloric acid and nitric acid, ionize completely in water. Weak acids, such as ethanoic acid, ionize only partially. Understanding ionization and basicity helps us predict the behavior of acids in chemical reactions. Concentrated mineral acids are highly corrosive substances and must be handled with great care. Hydrochloric acid, nitric acid, and sulfuric acid are among the most important concentrated acids used in industry and laboratories. Concentrated hydrochloric acid is a colorless liquid that gives off white fumes in air. It reacts with metals, carbonates, and bases much faster than dilute hydrochloric acid. Concentrated nitric acid is usually colorless, but may become yellow upon storage because it slowly decomposes to produce nitrogen dioxide gas. Nitric acid is not only acidic, but also a powerful oxidizing agent. Concentrated sulfuric acid is a colorless, oily liquid. Besides being acidic, it has strong dehydrating properties. It can remove water from substances and cause severe burns. Because of their corrosive nature, these acids carry hazard warning labels and require protective clothing, gloves, and goggles during handling. Laboratory safety is essential whenever concentrated acids are used. Let us now turn our attention to bases and alkalis. Bases are substances that neutralize acids. Most bases are metal oxides or metal hydroxides. Examples include copper 2 oxide and magnesium hydroxide. Alkalis are simply soluble bases. Examples include sodium hydroxide, potassium hydroxide, calcium hydroxide, and aqueous ammonia. Alkalis produce hydroxide ions, OH, when dissolved in water. These hydroxide ions are responsible for alkaline properties. Oxides are classified into 4 categories. Basic oxides are mainly metallic oxides and react with acids. Acidic oxides are mainly nonmetallic oxides and react with alkalis. Amphoteric oxides, such as zinc oxide and aluminium oxide, react with both acids and alkalis. Neutral oxides, such as carbon monoxide and water, do not behave as either acids or bases. Bases also react with ammonium salts when warmed, producing ammonia gas. This reaction is commonly used in laboratory tests for ammonium ions. Understanding these classifications helps us predict how different substances will react with acids and alkalis. Finally, let us discuss pH and indicators. The pH scale measures the concentration of hydrogen ions in a solution. The scale ranges from 0 to 14. Solutions with a pH below 7 are acidic. Solutions with a pH above 7 are alkaline. A pH of 7 indicates a neutral solution. The lower the pH value, the stronger the acid. Similarly, the higher the pH value, the stronger the alkali. Indicators are substances that change color depending on the pH of a solution. Methyl orange is red in acids and yellow in alkalis. Phenolphthalein is colorless in acids, but pink in alkalis. Universal indicator provides a range of colors corresponding to different pH values, making it useful for estimating pH accurately. In agriculture, soil pH is very important. Most crops grow best in soil with a pH close to 6.5. Acidic soils can be treated by adding lime, which contains calcium oxide or calcium hydroxide. This process is known as liming. To conclude, acids, bases, alkalis, and indicators play a vital role in